Hello everyone. This is a tutorial for Move Semantics, which is a feature that was added in C++11. This is going to be a live demo, which means I'm going to do all the coding as we go along, as I think it's very useful to see how the code evolves from scratch, and to keep the examples as minimal as possible, rather than presenting you with large slides with a lot of code where you're trying to quickly figure out which parts of the code are relevant. And there's going to be two things I want to emphasize in this training. The first is that I want to make it as intuitive as possible. And the way that I typically make things intuitive is that I take things that you already know and I just expand upon them a little bit. And the second thing is that I like to show some motivating examples and the reasoning as to why we want to use this feature, as opposed to just showing you the syntax. So we're going to start just by having a simple structure called foo, which for now is going to be completely empty. So the first thing we want to ask ourselves is, well, what does move semantics mean? In particular, let's look at the word semantics. Now, whether you refer to them using this name or not, you're probably already aware of two different types of semantics in C++. The first is value semantics, and the second is reference semantics. So this is value semantics, and with value semantics you can think we're going to make a copy, and there are reference semantics. So C++11 introduces a new type of semantics called move semantics, and I'm not going to show it to you just yet. We're first going to kind of build up by looking at these ones first. So the very first thing we'll do is we'll just have this foo, and this is not very interesting considering that foo is completely empty. So the first thing that we do to make this slightly more interesting is that we'll give foo ownership over some resource. In fact, we can say that this will start as null pointer. So we'll say that foo owns this integer 42, which is doing heap allocation, and we typically say that heap allocation is kind of relatively expensive. So when you look at this, we already have a first problem, where when we have ownership of resource, we need to make sure that we clean up the resource when we're finished with it. So you say, okay, well, that's pretty easy. I'll just have a destructor, and if I is not equal to null pointer, then I will delete I, and I'll set I to be null pointer. And that fixes that first problem. And then, since we want to start exploring these other types of semantics that we're more familiar with, we'll say, well, F2 is a copy of F1. And if you try and run this, you in fact have a problem, and it crashes. And the reason it crashes is that when you try to copy construct this F2 from F1, they both end up having this int pointer pointing to the same memory. And then when they get destructed, they're both trying to delete the same memory twice, which you can't do. And again, this is something fairly common, where when you have ownership of a resource, you need to define how this class does its copying. So in this case, we'll say if I want to copy something else and it has some resource, then I would like to have a copy of that resource. And then we also need to have a default constructor now, since we have a custom constructor defined. And we run this code. Now it's happy and it doesn't crash. So nothing new so far. But we're going to change this a little bit now. So what we're going to do is we're going to introduce another level of scope. So again, this is just trying to be a simple example. For different levels of scope, you could imagine that this exists in some some class that's a bit more persistent, and this is just like a temporary function that's doing some temporary work. So if instead I say f2 gets this resource and f1 becomes a copy of f2, the first thing I need to do is I need to implement this assignment operator. So I have assignment operator, which is going to do the same thing as this, except it's also going to return a reference to this. And I can run this code, and again, everything's happy. But not everything is quite happy. So now we get to the point where we start being interested in move semantics and what it can give us. So the problem here is that we have two heap allocations. We have this first one here when we're setting up f2, and then in this assignment operator, we have a second heap allocation. And the reason we don't like that is we know that foo2 is about to be destroyed, right? So foo2 exists only so that foo1 can become a copy of it. So we kind of think to ourselves, well, I want something that's slightly different than this copy assignment operator. And you can say, I'd like something that doesn't take it by const reference so that I'm allowed to mutate it. And instead of making a copy of that, I'll just steal ownership from the other one, right? So instead of making our own copy of whatever the other one had, we say, I'll point to what you owned, and now you don't own anything. And notice how I commented out this new now. So I don't have two news. I just have the one new. Well, the problem is I don't really want to destroy the copy assignment operator, because the copy assignment operator should make copies. So what we like to do is we want some sort of other function. So we'll restore this to how it was. But we want some new function that does this. And the way that we do this is we add a second ampersand here. And that double ampersand signals an R value reference, right? So this is not the binary, no, this is not the AND, not binary AND. This is not AND, like A and B. This is a new use for this double ampersand, which stands for R value reference. And I'm going to talk a bit about what an R value reference is. So to explain R value reference, we just look at a simple math equation. So we have 1 plus 1 equals 2. And in this equation, in math, you often have these two notations, LHS, which stands for left-hand side, and RHS, which stands for right-hand side. And 1 plus 1 is the left-hand side, because it's on the left-hand side of this equation, of this equal sign. And 2 is the right-hand side, because it's on the right of the equation. So in the same way, we have L values, which are kind of left values, and we have R values, which are right values. And the easiest way to think of that in terms of programming is that you have something like int I equals 42. And in this case, the I here is the L value, and the 42 here is the R value. But that's not strictly correct, because I could say, well, I can have just 42 and this compiles fine. And there's no equal sign anywhere here. But this is still an R value. For L values, the way that you can think of them is that they are permanent values, or they are values that have an address, right? Because you can take the address of I here, but you can't take the address of 42, because 42 is just a literal. There are also things that have an identifier, right? So I have no way to refer to this 42 in the future, because it has no identifier, whereas I can refer to this I anytime in the future because it has this identifier I. So by contrast, an R value is something that is temporary. And there's actually two types of R values. There are PR values, which are pure R values, and there are X values, which are expiring R values. Or I guess just expiring value. So we know that this F2 is going to expire. So rather than making a copy of it, we'd like to just steal its resources. So we can say we want to move its resources from F2 into F1. And there's two ways we can do this, right? So either we can have a pure R value, or we can have an X value, because we want to have an R value reference, right? Because we need to differentiate from this copy assignment operator, which is an L value reference. So there's two ways to do this. The first is kind of perhaps the more obvious one because of move semantics. So if you want to use this, there's a function called move that exists in utility, and I'm just going to use standard namespace here, right? So this is actually standard move. And I say, well, I'm going to make this F2, and it's going to do this expensive heap allocation, but then I'm going to move F2 into F1, which will allow me to avoid a second heap allocation because I'm going to steal its resources. And I'm just going to show you kind of the definition of move. And I don't expect you to understand all of this. It is quite confusing looking. But the important part to see is that it's a static cast to an R value type, right? So move isn't actually doing the move itself. It's just saying, hey, this L value here, I want to tell you that it's actually an expiring value. So you're explicitly saying, I know that this L value is about to die, right? Because F2 is about to go out of scope. So I know it's about to die. So I'm going to signal to you that you should treat it as an expiring value. So then we just want to confirm that we're actually using it as an R value reference, right? So we're doing the move assignment rather than the copy assignment. So if I run this, sure enough, we break here in the R value reference in the move assignment operator. So that's one way. So this is by X value. And there's a second way we could do it. So let's say we comment this out for now. The second way is we want a pure R value, right? So a pure R value is a value that doesn't have a name. The other way you can have a kind of pure R value other than a literal is you can have a function that returns a value. Return PR value, let's call it. And all it says is it returns 42. So if I do this, the result of return PR value is a PR value. This is also a PR value, and this is also a PR value. So we want to have foo as a PR value now. So the problem here was we had to make the foo first, and then we could assign the I. So what we can do instead is we can make a constructor for foo that takes an integer as its argument, and then it'll set up the integer based on what we gave it. Right? So now we have a constructor that takes the integer directly. So what we can do now is instead we can have f1 equals to foo 42, right? So we just kind of condensed these two lines into one. But it allowed us to remove this L value, because before we couldn't assign the value to I because we had no way to do so with a constructor. But now we can do it in a single step. So again, if I run this, if I fix errors, oh, I can't have this defined twice, obviously. Well, I guess I can leave it. call it I2. Again, here we land in the move assignment operator. So we have an R value reference. Right? So this here is a PR value. It's a pure R value because it has never existed on the left-hand side. It is just temporary, as opposed to in the first case where it was a left-hand side value, but we knew it was going to expire. So we said, I want to move assign you by turning you into an X value, right? An expiring value. So there's a few things you need to know about this. So let's delete all this for now. There are something called special member functions. So the special member functions are the default constructor, the copy constructor, the copy assignment operator, the move constructor, and the move assignment operator. Oh, one more. Actually, there's 6. Yes, there's 6. And the destructor. So there's 6 so-called special member functions. And these are special because if I didn't write any of this, it would be done for me anyways. The compiler will automatically generate these 6 functions. But there are some rules that are a bit funny about this. I suppose actually I am not going to list this. So there's actually 5, yes. You might have heard of something called the rule of 3. If you haven't heard about the rule of 3, it's okay, I'll explain it. And there's actually something new called the rule of 5, and it has to do with these special member functions. So the rule is that if you define any of these 3 functions, then these will not be defined automatically. And I'll explain the reasoning for this. The reasoning is that if your class needs a destructor, it's probably because it is managing some memory that it needs to delete. If it's managing some memory that it needs to delete, it probably also needs special handling for the move constructor, right? Because if you want to transfer ownership of the resource, you need to write some explicit code. So because this is a new feature, right, this didn't exist before C++11, they can't assume that when C++11 rolls around that they can suddenly make these for you, because it would be unsafe. So they said, well, if you had some sort of special treatment, we'll assume that it was not safe, so we won't generate these for you automatically. So if you have any of these 3, so the copy constructor is similar, right? If you have a copy constructor, it might be because you need to do some special resource handling, in the same way that a destructor needs to do some special resource handling. So if you defined any of these 3, then these 2 will not be defined, because they're probably unsafe in the same way. So when you want to have these move constructors, you're going to have to write them on your own. And there's kind of a case that is a bit more unfortunate. So let's say these didn't exist. Let's say you had a virtual destructor because you intended to use this class as a base class that somebody would inherit from. Well, the mere fact that you declared that there is a virtual destructor means that you don't have this move constructor. which could be a shame, because it's not true that every time you have a destructor, it's because of some resource management. You could also have a destructor simply because you want to be used in inheritance. So because you have this, you need to define these manually. And if you define those manually, I also need a default constructor. If you define the move constructor manually, it says, well, it's probably not safe to have a copy constructor. So these are all linked to each other. So here you can see, because I wanted to use this foo as a base class as part of inheritance, I had to manually define these move constructors. But because I manually defined the move constructor and the move assignment operator, I don't have a copy constructor, so I can't actually run this code, right? So here you can say the move constructor can't be referenced. It is a deleted function, because these get deleted by the compiler because these exist. So I need to define them all. And this is something that's called the rule of 5. And it was formerly the rule of 3. There's another thing that works, which is called the rule of 0. So they say, well, if none of these existed, like I said before, the compiler would generate all of them for you, right? So the rule of 0 works. The rule of 3 was before these move operators existed, right? So you'd have 3 things that you should define. And the rule of 5 is now that you have these move assignment and move construction, move constructor and move assignment operator. So let's look at another case. So this foo was kind of something I made up, but foo is not too weird. I mean, yes, it's made up, but it was just representing any kind of class that had ownership of some resource. So these are more common than you think. But just for fun, let's look at another case where move assignment or move semantics can save you a lot of resources. Or a lot of time. So let's have the same scenario, but with vectors. Right? So here it's not even a vector of foo. It's not even a vector of something that has a resource, right? These integers don't own any resource. So here, what is it that I'm saving, right? Because if the integers themselves, they're not integer pointers, right? It's not pointing, this points to something on the heap. But keep in mind that a vector has its storage on the heap, right? So all these integers, even though they don't have any resources of their own, they themselves are like the vector's resource. So rather than having v1 become a copy of v2, in which case it would have to allocate, a second set of resources on the heap, it can just gain ownership of it because I know that v2 is about to expire. And if you look at this vector, this is again going to be kind of confusing, but don't be frightened. I'm going to just show you quickly the move constructor. So if we can find it in here. Here we are. Here's a vector that takes my type by our value reference, and it just happens to call it right? Because it's like the right-hand side. And this is the part that interests us. Right, so actually it should be this is the one I should be looking for, the move assignment operator. But again, this is the key function that's calling. It's called assign r value. And if we look at this assign r value, no, that's not the one I would like. Hold on, let me just do it with this one. It's a bit easier to find. You can see that it is stealing its resources, right? So this is the new one, and it's going to point to the resources of the R value, and then the R value is going to get cleared. So right away we save again on doing heap allocations. But let's talk about yet another interesting scenario. So let's say foo had a vector of ints, but it also had a lot of expensive other data. So in particular, when you say a lot of expensive other data, pretend there's some class bar B, and B has some init function that's very expensive, right? So when you construct a foo, one of its members is a bar, and bar's constructor has some very expensive initialization. So also imagine we have some sort of function foo that is fill vector. It takes some vector of ints by reference, and let's say it conditionally fills the vector. We don't know what the condition is. So sometimes when you call this function, it'll put contents into V. Sometimes it won't put contents into V, depending on some variable we don't know. So we can have a foo, and then we can call fill vector with the foo's vector. And then we can say if the vector is not empty, then we do something. We don't care what we do. And we're not really having an else, but just to make this more emphasis, otherwise we made foo for nothing, right? Because we're not going to use it. Either we're going to do something with it if it's not empty, otherwise we made it for no reason. And the problem with this is if we made it for no reason, we had this very expensive construction of foo that we would like to avoid. So what we could do instead is we could just have a vector of integers, right? And then we can just fill that vector. And then if that vector is not empty, now we could make a foo. Now we could actually say we have a constructor for foo that takes a vector of int by reference, and it's going to use by R value reference, right? And it's going to use that vector. And then we say, I'll make a vector, I'll fill that vector. If it's not empty, then I'll make a foo with that vector. And then the key here is that we didn't make a foo for nothing, because we never made the foo unless it wasn't empty. But actually, when you look at this, there's something wrong here, and it's kind of amusing. So here, this V is an L value, but I used move to do an R value cast, which turned this L value into an X value, right? I said it's going to expire. Here it's going to expire for another reason. So before, we had something that was expiring because it was going out of scope. But here, I'm saying it's expiring just because I'm not going to use this V anymore. I'm going to transfer over its resources. So one thing that happens is that when you call move and you hand over the result to somebody, the V here ends up in what they call a valid but unspecified state. So what this means is you can't really use it. So I know that V is not empty, right? So you think I can call front on V, but you actually can't, because maybe this did something with the V, right? Maybe it tried to steal its resources. So this isn't safe, right? So not safe, because we're in an unspecified state. So we won't do that. But there's other things you can do. You can do things like vector.clear. And This is fine because it doesn't depend on the state, right? When you clear something, it doesn't matter. It doesn't matter whether it has something good or not inside of it. Because it's unconditional on its contents. But there's a problem here. So in this constructor, I'm taking this v, and it's now, one of my arguments. So it could be that I want to do things with v, right? So inside here, maybe I want to use v. But you can't use v if it's in an unspecified state, because it's not safe. So this v, which we're getting by our value reference, is actually an L value within the scope of this function. Right? So that allows us to do things like, well, I can look at the front of it, and maybe I can, I can push things into it. I don't know what I'm going to push, but let's say I was going to push something into it. I could erase something from it. Don't know what I'm erasing, but I could erase whatever. So I can use it multiple times, and it needs to be safe, because foo is essentially gaining ownership of this v, because I said, I'm done. I'm expiring. I'm giving myself over to you, so you can do whatever you want with me. But the only thing I want to do with this is actually give it to the vector's R value constructor, because it's not foo that wants ownership of this vector's resources. It's our internal vector which wants to gain ownership of this vector's resources. So what we actually have to do here is call move again, right? And it looks kind of funny because you're like, well, this is already an R value reference, and it sort of is, but it's sort of not. It's an L value within the scope of this. So you have to say, okay, well, I gained ownership of v, you gave v to this foo constructor, and I, as foo constructor, am going to give ownership of this v to this vector's constructor. Right? So this is a very key thing to note here. It's very important. And that'll just about cover it for now. Thanks for watching.